So thanks for coming for addressing class imbalance in machine learning. My name is Sara Garcia. I will be going a little bit faster because of this delay, so I hope you don't mind. So first of all, what is the class imbalance problem? This problem is when the data is not equally distributed. Okay. So sorry. Well, I was saying that the class imbalance problem is when the data is not equally distributed, and most machine learning classifiers they get biased toward the majority class. This is a big problem, and it should be a starting point whenever we are creating a machine learning model, because the most common problems in applications like fraud detection, medical diagnosis, or for example oil speed detection are very highly imbalanced. Usually for this type of data, we have a very large negative class and a very small positive class. We can see in this example, we can take, for example, that these are a problem of fraud detections. In this type of data set, we will have a lot of non-fraud transactions, and very few percentage will be the positive class, the class that we are actually want to predict. So in the first starting point, to address this problem, we should check the confusion matrix, and we can see that the accuracy for this type of problem here, like in here, if we calculate the accuracy of this problem, we can have, for example, being like 96% of our transactions are non-fraudulent transactions, and only 4%, for example, 4% are actually fraud. If we only build like an if-else statement, our classifier will be 96% of accuracy. This is not. This won't be any useful model. That's why the first starting point should be change the performance metric. For this, we have very different metrics. One of these is precision, recall, or the ROC, area under the curve of ROC. We have different performance metrics, and this should lead to less misleading results. So for methods for handling class imbalance, we have different methods that I have divided into the data level techniques, the model level techniques, and hybrid techniques. I will be talking first of the data level techniques. I will be talking about undersampling and oversampling techniques, and then I will move to weight balancing, ensemble learning, and I think that will be enough for this time. So for undersampling techniques, we have that in this type of for this type of techniques is what we do is to reduce the amount of the majority class. For majority class, we can have, we say that is a class that far exceeds the other, and the minority class is the class that we are actually trying to predict. So in this type of techniques, we are going to reduce the amount of the large class to help balance the data set. And on this, for these techniques, we have random undersampling, that is just randomly remove observations from the majority class. We have Tomek links is another technique, and cluster centroids. I cannot speak with the details because the limited time, but is taking a consideration the space between the, we can have a consideration the space into the for the reduction of the data. And one of the advantages of this type of techniques is that because we are going to reduce the amount of data, we also, that means we don't need the same amount of computing resources, so it implies a reduction of the memory. And for the disadvantages of this type of technique is that there is a high risk of removing useful information because we are deleting examples. And this type of observation that we are going to remove, they may not be they may not be an accurate representation of the whole population. We are, if we remove data, we are going to change the distribution of the data as well. So another technique is oversampling, and with this technique, we are going to replicate observations from the minority class to balance the representation of the class. So this means that we are going to increase the minority class here to make a more balanced data set, and with this the model will have enough equal amount of data to learn. For this type of techniques, we have random oversampling, which means that we are randomly choose examples and we replicate them. We have smooth and adasing. I don't know if I'm pronouncing very well, but for one of the most used technique of oversampling is smooth, and I'm going to talk about it a little bit. And one of these advantages of this technique is that we don't remove any example. That means that we keep all the information. No information is lost. So we have as well disadvantages, and one of the disadvantages is that this type of techniques they increase the probability of overfitting because we are going to replicate observations from the actual data, and the size of the data augments. That means that we will have to use more computation, and just to leave this these two techniques, we can consider it if we have a data set that is quite large. We can consider use undersampling techniques to balance the data set, or in the case that we have a very small data set, we can consider it as well undersampling. There are also different types of undersampling and oversampling techniques, and that one of them are, for example, stratified sampling, and well, there are a lot, but it's we can consider more non-randomless, randomless, and the one important thing when we are doing these changes on the data set is to always resample. Do the resample in the training data, not in the validation or testing data. This is very important. I'm going to leave a little bit of code from the source, from the documentation. To use this, we can make use of the imbalance learn package. We can do it with conda or pimp install. And here is an implementation with very simple implementation of undersampling of the data set. And as you can see, it's very easy and straightforward to use. For another techniques are a mixture between undersampling and oversampling. And with this type of techniques, the more used is the smooth. And this techniques is about creating synthetic samples and creating new samples for the minority class and undersampling the majority class. So if one of the large methods for synthetic sample creation is smooth, that consists in having these the black dots being the minority class samples. So we first compute the distance between the k neighbors, and we will create a new sample between the distance vector, and that's this will generate with this technique. We generate new samples of the minority class that are different. So in a way, we can eliminate reduce the probability of overfitting. And one of the advantages of this is this technique is that we are creating new samples. We are not just copying them, they are new. And the disadvantages is that this, as we can see here, by creating new samples, we are not considering that they may overlap to one of the majority class. For example, we can create one sample, generate one sample from the minority class, and that sample may overlap a sample that is part of the majority. That is one of the biggest disadvantages of this technique. The implementation is as well we can install the imbalance learn package, and with this package it's just about calling importing smooth from the oversampling package, and as you can see, it's very straightforward as well to implement. We can also implement a lot of variation of this algorithm in Python. And another type of techniques is the model-based techniques. One of these techniques is class weighting, and the other one is the ensemble of classifiers, also known as ensemble learning. And for class weighting, the thing we're going to do is to add weights to the observations of the minority class, and we do this what is the word? To penalize the model to learn the minority class examples. And another method is the focal loss method. And this method was developed last year, I guess, by Facebook. And what it does is that it will it will give lower weights to the observations already that are correctly trained, and it will give higher weights for the examples that are harder to learn. And for the other techniques is the ensemble of the classifiers. And with this, there is a lot of literature here, but what we do here is to combine models, and there is different type of topologies. One of these is cascading, parallel, and hierarchical topologies. And for the cascading topologies, it's just one model after another. So the output of the first model will be the input of the second model, and so on. And for the parallel topology, we'll have that there are several models that will be given the same data, and we do a decision logic here that can be for voting decision, for the mean, or etc. There are a lot of ways to classify here, to decide the actual classification. And for the hierarchical topology, we have is a combination of the first two, and as well we do here a combined a decision logic for combine the final prediction. And another techniques is boosting, aggregation, also known as bagging. With this, the classifiers, all the classifiers are given equal weights, and the predicted class is chosen by the majority voting. And we can see here, we do several splits on the data, on the data sets, and all these sets are fed to the different classifiers, and the actual predicted, the prediction will be the majority prediction of all the models. For example, if our model C1, C2 predict, for example, that the class is the example is class A, for example, and the rest three are predicting that the class is B, then the final classification will be class B because is higher. The majority of the models predicted that the class is B, so our final model will predict class B. One of the advantages of these techniques is that it is very useful with when the data is limited, and it works better when the base classifiers are unstable. This means that they will reduce the variability of the data, and we have less probability of overfitting because of the reduction of this variance. And for the disadvantages of this technique is that it's not suitable when the computation resources are limited, because as we can see, we use multiple classifiers, and each of these classifiers require a computing resource. So we have to take into consideration this as well. And we may lose interpretability of the model at the end. It's not very straightforward to describe how is the decision rule of the ensemble of the whole system of models. And another technique, this is very used, is boosting, and it's quite the same. Quite the same strategy, with the difference that we add weights to each of the classifiers here, so we can have higher weights to the classifiers that are predicting well. For these techniques, one of the best known is AdaBoost, and we also have gradient boosting. There's a lot, as I said, there's a lot of literature here, a lot of different combinations and different models here. And for the last technique is the composition of the two previous techniques. Is hybrid strategies that consist in combining data sampling, like oversampling or undersampling, with the combination of classifiers. And with these techniques, we have like easy ensemble, balanced cascading, smooth boost, and so on. There's a lot of techniques here. So for the final words, I just have like 4 minutes. First, you have to check your confusion matrix always. That will be like the first step. Go into the data, and then we have to consider it as well, the computing resources. That's very important, especially with deep learning, because computation is expensive. If we have a small data, we can use oversampling techniques. We can use stratified sampling or modes. And for large data, we can consider use undersampling, like near miss or Tomek leaks. We also can consider it if the data we have is high with high variance. We can consider using bagging methods. Or if the model we have is biased, we can consider using boosting methods. I think that's enough. I have just like, I don't know how much time to questions, no?